EMG question of the day. Which is the most likely pathogenesis of this type of spontaneous potential? A. Axonal hyperexcitability. B. Ephaptic activation of neighboring muscle fibers. C. Ephaptic activation of neighboring axons. D. Ephaptic transmission from type 2 efferents to static gamma and beta efferents. The spontaneous activity presented in this question corresponds to complex repetitive discharge. Complex repetitive discharges are not associated with any clinical manifestation. The sound generated during EMG recording by this activity resembles the sound of a motor of a boat, an idling motorcycle, or the firing of a machine gun. This is so because of its repetitiveness and its abrupt starts and endings, as well as sudden drastic changes in the quality of the sound, as you will hear in the next frame. The striking visual feature is its exquisite fixed repetitiveness. This quality is emphasized in the bottom tracing. In the bottom tracing, the 5 running potentials from above are superimposed. In this frame, I have isolated the top tracing, which I intend to use to explain the genesis of each wave. Here you can see 9 muscle fibers. These fibers are denervated, but in addition they have a set region of lowest threshold for activation. These regions are represented in red. They are the site where ephaptic transmission of electrical activity goes from one muscle fiber to the neighboring muscle fiber. In this frame, I have added an asterisk at the lowest threshold region of fiber 1. I have done so to indicate this region as the pacemaker or ringleader. Now I have introduced a monopolar needle tip to start explaining the process that most authors believe causes complex repetitive discharges. The green burst in muscle fiber 1 indicates the occurrence of action potential. The arrows just introduced illustrate the bidirectional progression of the action potential. Notice that when the traveling action potential encounters the lowest threshold region of the second muscle fiber, the electrical activity advances in that direction, as indicated by the turn arrow. This frame illustrates 2 significant events. One is the occurrence of an action potential at the lowest threshold region of muscle fiber 2, illustrated by the aqua burst. As I have just told you, this action potential is triggered by the arrival of electricity from fiber number 1. The second significant event is that the action potential in fiber 1 reached the electrode. It is the arrival of this potential to the cache area of the electrode that produces the first wave, which I have highlighted in green, matching the color of the arrow in muscle fiber 1. Milliseconds after the potentials in the first and second muscle fiber advance. In this frame, in fiber 1, I have only represented the action potential traveling away from the needle because the one traveling towards the needle has already passed the electrode recording area. Not drawing the arrows once the action potential past the cache area of the needle will also be followed for other fibers in the course of this explanation. The action potentials continue to advance. In muscle fiber 2, the potential traveling towards the needle reaches it, as you can see here. The second wave is thus recorded. With further advancement, the action potential in the second muscle fiber is transmitted ephaptically to the lowest threshold area of muscle fiber 3, and an action potential is triggered. Now the action potential advances in all 3 fibers. As the advancing continue, the lowest threshold area in muscle 4 is reached, and an action potential is triggered. While the action potential advances in fiber 1, 2, and 3, few milliseconds later, the action potential traveling in muscle fiber 4 activates fiber 5. At the same time, the activity traveling in the direction of the needle in muscle fiber 3 reaches it, and a new wave is recorded. Subsequently, an action potential is triggered in fiber 5, followed by advancement of the action potentials with activation of the lowest threshold area of fiber 6, triggering an action potential in fiber 6. The advancing action potential in fiber 6 spreads to fiber 7 and it becomes activated. The action potential now advances in fiber 4 to 7. the action potential in fiber 7 traveling away from the needle is transmitted to fiber 8, triggering an action potential in this fiber. Next, the action potential continues advancing. The lowest threshold area of fiber 9 is excited, and the action potential of muscle fiber 4 reaches the needle, generating a new discharge. Next, action potential occurs in fiber 9, and the action potential in fiber 5 reaches the recording area of the electrode, triggering another wave. Milliseconds later, the action potential of the 6th muscle fiber reaches the electrode recording area and a new wave appears. Further advancement potentials in fiber 7, 8, and 9 continue, and the action potential in fiber 7 reaches the needle recording area, generating another discharge. Shortly after, the fiber 8 action potential reaches the needle, as indicated here, triggering another discharge, and finally, the action potential in muscle fiber 9 reaches the needle, generating the last potential of the group. But how does it repeat? To explain this, let's go back in time to when the action potential in fiber 9 was about to reach the needle. As you can see, I have added an arrow indicating the reactivation of the pacemaker. This is possible because the muscle fibers involved in complex repetitive discharges are not arranged in parallel as represented here. They are arranged as I have represented them now in this new frame. In this frame, I have drawn a transverse cut of all the fibers arranged in a group, which is how they are in normal life. Hence, fiber 9 and fiber 1 are abutting, so the electrical activity as illustrated in this frame can ephaptically be transmitted, as represented by the small blue arrow indicated in this frame. Yet, questions remain that have received logical but unverified answers. Why do complex repetitive discharges stop abruptly? The current accepted answer is that the pacemaker muscle fiber fails to initiate an action potential, either as of ionic changes or a block. Why do complex repetitive discharges abruptly change discharging pattern? In this frame, you can see 3 transitions as the result of a change in the excitatory circuit. Here, 1 muscle fiber is left out. Here, 2 muscle fibers are incorporated in the circuit. And here, 1 fiber is left out, the same fiber as at the beginning of the trace. The validity of this explanation that ephaptic activation of neighboring muscle fibers is the mechanism producing complex repetitive discharges rests on complex repetitive discharges being generated and originating in group muscle fibers, hence persisting despite physical or chemical denervation. Yet some researchers have found that some complex repetitive discharges disappeared following denervation with curare, and developed 2 different hypotheses to explain this phenomenon. The first one involves the spindle and consists of ephaptic transmission from type 2 efferent to static gamma and beta efferents, as illustrated here. The second hypothesis was put forward in 2020. It states that complex repetitive discharges may result from myoaxonal re-excitation in sprouting motor units. These 2 hypotheses are not as widely accepted as the first explanation. So the answer to this question is B. Thank you very much for your attention.